This is part 5 of the series Logarithmic, Exponential, and Other Transcendental Functions. And in the last part we were doing some examples for logarithmic integration, and now we're going to continue with some more examples in this part. And the first example we have is the integral of x plus 1 over x squared plus 2x dx. Hopefully we can see that this numerator is going to be part of the derivative of this guy here. So let's take our u to be x squared plus 2x, and our du becomes 2x plus 2 dx. Now you can see that this is a factor of this. So we just have to pull out a 2 here, and we have 2 times our numerator times dx. So if we divide out that 2, we have our numerator and the dx matched with du over 2. So our final integral becomes the integral of 1 over u, that's 1 over, this is our u, times du over 2. Pulling out the 2 outside the integral sign, constant multiple rule, we have 1/2 the integral of 1 over u du. And as usual, that's just 1/2 the natural log of the absolute value of u plus c, and then we simply back substitute. Take our u, put it back in here, and there's our integral. Now you might be tempted to say, well, we have this 1/2 outside here, let's make that a power. And you might even be erroneously tempted to say, oh, that's just this squared. Well, actually, that wouldn't be the case. This would be the 1/2 power, so that would be the square root of this thing. But that's not going to really bias anything in simplification, so the best thing is just to leave it as it sits here. Now we'll move on to our next example. Now here we have our next example, and hopefully at this point you can start to see some patterns developing. If you pick this as your u, you're going to have an additional 3 out here that you're going to pull outside, and you should be able to start to see some of these things recurring over time. So let's go ahead and look at the solution of this. And so if I take 3x plus 2 as my u, my du is 3 dx, pull out the 3, and we have dx is du over 3. So my integral becomes the integral of 1 over u, since this is my u, that's my u, it's 1 over u du over 3, pull out the 1/3, we have the integral of 1 over u du, which is, as usual, the natural log of the absolute value of u plus c, and then we go ahead and back substitute our u in here, and we're done. Alright, let's move on to another example. Now here we have another curious problem. I would encourage you to take a look at this for a second and see if you could figure out what the right first step would be. If you thought to take either one of these as your u, you might have a bit of an issue because neither one is the derivative of the other. And so we have a little bit of an issue. Now, in this particular case, we can always do what the function implies. This is a rational function that says this divided by this. So what I'm going to do is I'm going to go ahead and do that division and see if we get a simplified version. Here we have, I took this value, pulled it out front, and I added a center term. We have a squared term, then we need a linear term, and I made the coefficient 0 just because we added in there for division purposes. And this is simply polynomial long division, and we put the numerator inside, and so we're dividing this by this. So what do we have to multiply x squared by to get x squared? That's 1. So we multiply through, and we get we get x squared plus 0x plus 1. Change the signs of all these and add. This becomes 0, this becomes x, and we have a 0 again. This x squared doesn't go in here, so we're done with the division, and the division is 1 plus x, the remainder, divided by the divisor. So that is our final quotient, and that becomes our new integral. The integral of 1 plus x over x squared plus 1. And as you can see, this is a derivative of this. So if we take this as our u, our du becomes 2x dx. We pull out the 2 as usual, and we have the following. This is the integral of 1 dx plus 1/2, we pulled out that 1/2 here, times the integral of 1 over u du. So this is the u, so it's 1 over u, and du is x dx. And then, as usual, the integral of 1 is x, because we're integrating with respect to x, plus 1/2. This is the natural log of u, absolute value of u plus c, and then we just back substitute here for our u. So this was our u, put that back in here, and this is our final version. So a little bit different. Just look out for having to manipulate before you actually take your integral or find your u and du values. So let's go ahead and look at one final function before we get into trigonometric functions. Now here you might think we have a peculiar thing, but again, what you're looking for is a u du situation, and in this case the best thing to do would be to work the inside of this composite. So we're going to start from that perspective. If I take my u to be x plus 1, then my du is dx, so that's matched. But now we have an issue because we have this 2. That's easily accounted for because we can just pull out the 2. But we have this x. So remember what we did in the past. We had to solve this equation for x. So we subtract 1 from both sides. U minus 1 equals x. So to match these, the 2 comes out. The x becomes this. So it's u minus 1 times 1 over u, because this is u squared, because that whole thing is squared. And du is dx, so du. Now we're going to combine these two things. So u divided by u squared is 1 over u minus 1 times 1 over u squared, which is 1 over u squared. And then I'm just going to manipulate this a little bit. You would think that we'd have another natural log, but not, because this is not to the 1. Therefore, we can do the power rule with this guy in integration. So let's go ahead and integrate. The 2 stays outside. The integral of 1 over u du is the natural log of u. And the integral of this, using the general power rule, is this guy. So these signs change because we're going to add 1 to the exponent, which is negative 1. And then we're going to divide by that new exponent. So a negative u divided by negative 1 is a positive. And so we have 2 times the natural log of absolute value of u plus u to the negative 1 plus c. And then we just back substitute our u's, which is x plus 1. And there's our final result. Just be cautious, take this one step at a time, and you won't have a big issue, but try not to jump to conclusions when you see these values. Just look at them for what they are and try not to read anything into them. Alright, now we're going to move on to the integrals of trigonometric functions. And I'm sure you've been looking forward to that. In looking at the trigonometric functions, we're going to start with the first 2 basic ones, sine and cosine. So let's take a look at how we do the integral, how we derive the integral of sine. Now we're going to use the idea of derivative. Since the derivative of cosine is negative sine, then by the fundamental theorem, the integral of sine must be negative cosine. And we're going to do the same basic idea with cosine. And we're going to look at the derivative. Because we know that the derivative of sine is cosine, then the integral of cosine must be sine. So these are our 2 basic facts. So the integral of sine is negative cosine plus c, and the integral of cosine is sine plus c. Now this can be confusing at times because notice in the derivative of cosine is negative sine, but yet the integral of cosine is positive sine. So everything's kind of backwards when we're looking at this from a sine standpoint. And we're going to see that reverse nature for several of the other ones. Now we're going to take a look at tangent, but with tangent we're going to do a little bit more of a derivation of that. So to investigate the integral of tangent, we can rewrite it, because tangent is just sine x over cosine x. And then if we take our u to be cosine, our du becomes negative sine. And so we pull out that negative sign out front. This would be the constant multiple rule. And we end up having negative integral of 1 over u du, because if our u is cosine, that's 1 over u. And so we have, as a result, the natural log of u plus c, and u is cosine. So the integral of tangent is the negative natural log of the absolute value of cosine plus c. Probably not what you were expecting. And the rest of these are probably not going to be what you've been expecting. They're all going to be versions of this natural log idea. Now in the derivation of the integral for secant, it's kind of bizarre. What we're going to end up having to do is we're going to multiply and divide by something that looks a little strange. Now there's a reason for this, because what we have to do is we have to create a substitution situation that's going to allow us to take this integral. And so the multiple is secant x plus tangent x. And if we multiply out of this numerator, we have secant times secant is secant squared, and then we have secant times tangent is secant tangent. And then the denominator becomes secant x tan x. Now you can see that the derivative of secant tan, you know that the derivative of secant is secant tan, and the derivative of tangent is secant squared. So this derivative is this numerator. And that was the whole reason for building in this strange sequence up here. So with this multiple, our u is secant x tan x. The derivative of secant is secant x tan x, which is this piece. And the derivative of tangent x is secant squared x, which is this piece. So here we have our u, so this is 1 over u, and our du is simply this numerator with the dx outside. And that gives us the integral of 1 over u du, which is the natural log of the absolute value of u plus c. And then when we back substitute, we're back substituting this u term. So the integral of secant x dx is the natural log of secant plus tangent x plus c. Now this might not be too hard to see because there's a relationship between secant and tangent. So you might want to try and come up with some memory pattern that relates secant tangent with secant. Alright, let's look at the next one. Now for cosecant, we're going to have a very similar derivation that we had for secant, but as with the cosine and sine and tangent, everything seems to be the negative of each other. So if this integral is the natural log of secant tangent, this is going to be the negative of the cofunctions, because secant and cosecant are cofunctions. So this integral is the negative. Cosecant is the cofunction of secant, cotangent the cofunction of tangent plus c. So this is just the negative of the cofunctions of these. And that's an easy way to remember these two integrals. And then finally, let's look at cotangent. Again, that's going to be the cofunction of this. So you can probably see that this integral is probably going to be something like the natural log of the absolute value of sine. And in fact, that's what it is. So these, again, are cofunctions of each other, and so too are their integrals. They're cofunctions. And they're also negatives of each other. This one's the negative, and this one's the positive. Here's a table summarizing results, and I would strongly advise that you commit these to memory somehow. A lot of times it helps to look at the derivation to assist in that memorization process. I'm going to wrap up this video, and we'll start the next video with some examples of trigonometric integration. And I will talk to you in the next video.